Welcome back. So today what we're going to do is we're going to prove one theorem about some kind of inequality result, which is the last thing we talked about last time. And then we're going to move on to divisibility. Okay, but one thing I realize is that I'm really not following the same organizational structure as the book in chapter 3. So in chapter 3 in your book, each section is devoted to like a specific proof technique, right? So 3.1 is on direct proofs, 3.2 is on more techniques, 3.3 is on proof by contradiction, 3.4 is on using cases, something like this. That's not the way that I've been doing it though, right? So what have I been doing in chapter 3? Well, first I introduced the technique of direct proof, but then we started talking about axioms of the real numbers and then proving things about the real numbers, right? And the point is that as I was going through these, I just used techniques as I needed them. In other words, I was covering mathematical topics, and the proof techniques, whenever I needed one, I would introduce it. So instead of trying to organize these things by technique, I'd rather organize them by topic. So because of this, I'll just call this chapter 3 continued, and I've relabeled these tabs you see. So let's say that this is just the third lecture on chapter 3. All the material is from chapter 3, just in a different sort of presentation order. Okay, so the first thing I want to prove is, as I said, a theorem about inequality. In order to do this, though, I'm going to use the results of a homework exercise, which you will prove. Okay, so because you will prove it, I will get to assume it for this lecture. So this will be proved on a problem set. You'll prove this from the axioms. Which is following: let a be a real number such that 0 is less than a is less than 1. Then 0 is less than a squared is less than a. So if you take a number between 0 and 1 and you square it, it ends up between 0 and a. Okay, so technically I haven't defined what this means. This just means 0 is less than a and a is less than 1, which hopefully you knew. But we only defined the less than symbol on two numbers, right? But you can string them together. That just means a series of AND statements. So when you prove this, you will assume that 0 is less than a and a is less than 1, and you'll prove that 0 is less than a squared and a squared is less than a. Okay, but because you'll prove it, I will assume it. In order to prove the theorem that I want to prove today, which is the following: the integer 1 is the smallest positive integer. The smallest positive integer is the integer 1. Okay, so let me first make a comment on the way that I've stated this theorem, which is I started the sentence with the phrase the integer 1. This is because I'm trying to avoid starting a sentence with a number or a symbol. So when you're writing formal mathematical writing, at all costs, you should try to avoid starting a sentence with a number or a symbol. This is just a stylistic thing. And so, a perfectly good English sentence is 1 is the smallest positive integer. If I removed the two words, the integer, at the beginning of this sentence, it would still be a good sentence. But it wouldn't be so great for formal mathematical writing because it would start with a symbol. So if you find yourself writing a proof and you've started a sentence with a number or a symbol, you should try to rephrase or add some words to avoid that if possible. Okay, someone's got to tell you it, so I figure I'll tell you it. In order to prove this result, that 1 is the smallest positive integer, I'm going to introduce a new proof technique, which is called infinite descent. Okay, an infinite descent is a technique to prove that something does not exist in a well-ordered set. Okay, what is a well-ordered set? A well-ordered set is just a set with some notion of less than, such that every non-empty set has a least element. So the one that we know about is the positive integers, right? So 14 was called the well-ordering property, axiom 14. If S is a set of positive integers and S has a minimum element, this means that the positive integers are a well-ordered set. So really, it's the only well-ordered set we know about right now. Which is good because in this theorem, I'm trying to prove something on positive integers. So I will have a well-ordered set. Okay, and how does this technique work? So it is a proof by contradiction, just a special kind, right? So suppose for contradiction that the thing does exist. And the technique here is, since we have a well-ordered set, we'll let X be the smallest one, right? Because we're in a well-ordered set, we have a notion of a less than. So we suppose the thing exists. Maybe there's more than one of that thing that has that property. We'll pick the smallest one. And then the contradiction that we'll get is to find a smaller one. This is a contradiction. And so it must not be true that the thing exists. Okay, so let's think about how we could use this technique on this theorem. This theorem is asserting that 1 is the smallest positive integer. So what I can do is I can suppose that I have an integer that's a positive integer that's smaller than 1. Let's take all the positive integers that are smaller than 1 and take the smallest one out of all of those. If I can find a smaller one that's still a positive integer less than 1, then that'll be a contradiction. And that's the technique that we'll use. Okay, so maybe just start this on a new page. So 1 is the smallest positive integer. Notice that here I'm being a little bit informal, but you have it written formally in your notes. So here's the proof. Okay, so infinite descent is a contradiction style proof. So suppose for contradiction, let's say we will prove this by contradiction. I want to do a little bit more setup first. But I'm just telling my reader that they should expect a contradiction proof. So how do I want to set this up? Let's let S be the set of positive integers which are smaller than 1. Right, so i.e. S is the set of all integers that are positive. And let's use a different variable here because I want to use X in a second. The set of all positive integers that are less than 1. Okay, and let's suppose for contradiction that S is non-empty. So I'm supposing that I have some positive integers that are less than 1. Okay, now since this is a set of positive integers, by the well-ordering property, by axiom 14, S has a minimum element. Let's call it X. So I'm following this technique of proof by infinite descent. Okay, well, since X is an S, we know that 0 is less than X is less than 1 because it's a positive integer that's smaller than 1. But by positive closure, X squared is positive because it's X times X. It's also an integer by closure of the integers. So if X is a positive integer, its square is also a positive integer. And now I want to use my previous theorem, which you're going to prove on a problem set, which actually holds for all real numbers, but in particular holds for integers. If x is between 0 and 1, then x squared is between 0 and x. So by the previous theorem, since 0 is less than x is less than 1, therefore 0 is less than x squared is less than x, but also x is less than 1, right? Hence, x squared is between 0 and 1. Now, x squared is an integer that's between 0 and 1. Therefore, x squared is an s, but also x squared is less than x, which contradicts that x was the smallest element of S. This contradicts the minimality of x in S. Right? X was supposed to be the smallest thing in S, but I found another thing in S that's smaller than x. This is a contradiction, which means that S must be empty, which means that 1 is the smallest positive integer. Hence, S is empty. So 1 is the smallest positive integer. There's no positive integers less than 1. Okay, so nice little technique here. Again, this will come in handy probably as soon as even 327, and probably also later in this course. But okay, so the reason that I wanted to prove this is actually for the next topic, which is on divisibility, which is also contained in chapter 3 of your textbook. Let me make the definition here. So a non-zero integer m divides an integer n if there exists an integer q such that n is equal to m times q. Okay. We say that m is a divisor, or sometimes a factor of n. We say that n is a multiple of n. I mean, if this holds. If m divides n, you say that m is a divisor of n, and you say that n is a multiple of m. And then also, this definition I made only for non-zero integers. So we'll just say that the integer 0 is not a divisor of any integer. Okay, so the reason I need to say this is because technically, like 0 equals 0 times 3, which makes it seem like 0 is a divisor of 3, or 0. Sorry, 0 is a divisor of 0, right? This is like the m, this is like the q, this is like the n. But this definition we only made for non-zero m. So I'm not going to say that 0 is a divisor of 0. I'll just say that 0 is never a divisor of anything. So this is just a technical point in order to complete this definition for all integers. Okay, but hopefully you have been using these terms, divide, factor, divisor, multiple, for a long time. And I just want to point out that you've been using them correctly since you were very young. Okay, so for example, 7 divides 21. Hopefully that's a thing that makes sense to you as a sentence, because 21 is equal to 7 times 3. There exists an integer q such that 21 is 7 times q. right? 28 is 7 divides 28 because 28 equals 7 times 4. So you would say that like 3 is a divisor of 21. Okay, maybe, okay, 7, but multiplication is commutative, so also 3 is a divisor of 21. 21 is a multiple of 7. My point here is just that this definition captures exactly the notion of divides, divisor, multiple that you already know. Okay, but I do want to introduce some new notation, which is probably new, which is if A divides B, we write A vertical line B. Okay, so this notation here means A divides B. Okay, notice that this symbol is not the same thing as a fraction bar, and it's not the same thing as an absolute value symbol. Right, so to write a true fact, 7 divides 21, that's a full sentence. That sentence says 7 divides 21. That sentence is true, right? If you're using a fraction bar, right, something like this, what is this? This is not 21 divides 27. This is 21 divided by 7. Here, the bar you're using to notate an operation that you're doing to the two numbers, and this is just equal to the number 3. Right, so even though you're using kind of a bar here and a bar here, the first bar is a statement about the relationship between 7 and 21. The second bar is an operation that you're doing on those two numbers. Okay, and then also the absolute value bars. These are delimiters. In other words, these need to always occur in pairs. Right, so the absolute value bars occur in pairs with something in between them. The divides bar occurs always by itself with a number on either side. Which means also that these are different symbols in LaTeX. Okay, so to produce this one, you use \mid. To do this one, you use the vertical bar key on your keyboard. But they are different. Okay, and I know several professional mathematicians who will remain nameless who use these symbols, who type them incorrectly, and it looks okay, but it's wrong. Okay, so I would prefer if you would type things correctly. And, you know, I'm sort of a pedantic person. Probably you could even tell even from just these recorded lectures. But that's enough about my personal failings. Let's prove some basic results about divisibility. Okay, so first theorem. For all non-zero integers A divides A. So not a particularly profound statement. Hopefully this is, I mean, you knew this already, but for one thing, let's talk about how carefully you need to write mathematical statements. So for example, if I remove this word non-zero here, technically the theorem is false, because if you let 0 be A, we've already said that 0 is not a divisor of any number. So technically, if you leave off like one little thing, you've written a false statement. If we go back to this definition of divisibility, by the way, if at some point, if you left off this word integer here, the definition would be completely different. So let's say this definition said m divides n if there exists a number q such that n is equal to m times q. If that were your definition, then, for example, 6 would divide 20, right? 6 would divide 20 because 20 is equal to 6 times 20 divided by 6. So there does exist a q, it's just not an integer. Okay, so you want to be really precise in what you're writing, because if you write something slightly imprecisely, you're actually completely wrong sometimes in mathematics. Okay, but proving this theorem Shouldn't be too difficult because all we have is the definition. Okay, so let's let a be a non-zero integer. I want to prove that a divides a. Well, what does that mean? To say that a divides a means that you can find an integer q such that a is equal to a times q. But we know such an integer, right? You can take q to be 1. How do I know that a is a times 1? That's by the identity axiom. So by the identity axiom, a is equal to a times 1. We also said that you can assume this axiom for the integers. If you go back all the way to our first lecture here, right? The blue line on the side here, you can assume those for the naturals. The green line you can assume for the integers. So you can assume axiom 5 for the integers with z replaced for r. So technically axiom 5 says that 1 is an integer. So also axiom 5 says that 1 is an integer. There's a multiplicative identity in the integers. Hence, by the definition of divisibility, a divides a. That's by definition, because we've shown that it satisfies the definition. Okay, so not a particularly complex proof, but just one that uses the definition. It's a thing that we should know why each step is justified. Let's prove the next theorem. So let a, b, and c be integers with a and b non-zero, because I want to say that a and b divide stuff. Okay. If a divides b and b divides c, then what do you think you can conclude here? So hopefully you said that then a divides c. Okay, so one nice thing about this class, this intro to proof class, is you already know quite a lot about divisibility, real numbers, integers. And so this theorem is not surprising to you, right? You basically already know how the math works. What the skill that we're working on in this class is how to prove things rigorously. Okay, so for example, at lots of other places, including where I went to undergrad, the first linear algebra course you take is the first proof-based course. Okay, and I know at UW in 308, there are proofs in 308, but you're not required to write proofs. Right? There are some proofs that your professor probably did at the board, but you didn't have to write any proofs. Okay, because if you're taking linear algebra as a proof-based course, there's 2 new things you need to learn. You need to learn linear algebra, and you also need to learn how to prove things. And so things can get more complicated because sometimes you're confused because you don't know how to prove something. Sometimes you're confused because you don't know the linear algebra. But when you have an intro to proof class like we do at UW, you know about how divisibility works, basically. So that the math part is clear already to you. And what we're working on is the how to prove things part. So it's like you can distill just that skill, which is one of the benefits to this course. It can also be a drawback because you sort of know too much. And so you're like not sure when something is obvious or not. But, you know, there's different benefits and drawbacks to any way to design a course. But let's prove this. Okay, so this is an if-then statement. So let's just prove it directly. Okay, so let's suppose that a, b, and c are integers, and a and b are non-zero. So if I'm doing a direct proof, I get to assume p and try to prove q. So if a divides b and b divides c, then a divides c. Let's suppose a divides b and b divides c. Well, what does this mean? The only thing I have at this point, basically, is the definition of divisibility. So by definition, this means there exists a q, an integer, such that b is equal to a times q. That's what it means to say that a divides b. And to say that b divides c means that there's an integer r such that c is equal to b times r. That's just the definition of a divides b and b divides c. What do I want? I want to show that a divides c. So we want an integer, let's call it n, such that c is equal to a times n. But again, you basically know how this proof should go, right? What n will work? I guess q times r should work. Okay, so maybe this is just an aside to myself, just to know what I'm aiming at. So now by substitution, c is b times r, but b is a times q. So c is a times q times r. And now by associativity, c equals a times q times r. And by closure of z, q times r is an integer. Right? It is important that I make sure that q times r is an integer, because the definition of divisibility says that there's an integer n such that c is equal to a times n. And again, if you don't require it to be an integer, then every integer would divide every other integer. But now what I've done is I've found an integer, q times r, such that c is equal to a times that integer. So by the definition of divisibility, a divides c. That's by definition. Okay, so again, you know how to prove this statement. Right? You probably knew how to prove the statement before I wrote this proof. And that's a good thing, because you know how the idea should go. You just want to be really careful in writing it up such that every step is justified. Okay, now the last thing I want to talk about today is sort of a little preview of what we'll talk about next time. So let's just call this part evens and odds. What's the definition? So let n be an integer. We say that n is even if there exists an integer k such that n is equal to 2 times k. We say that n is odd if there exists an integer k such that n is equal to 2 times k plus 1, if it's 1 more than 2 times k. Okay, so let me make some comments on this definition. Okay, so first of all, the definition of even, you could just as well say that if 2 divides n. N is even if and only if 2 divides n, because the definition of 2 dividing n is exactly there exists an integer k such that n is equal to 2 times k. So you could say, we'll say that n is even if 2 divides n. That's equivalent to this definition. Okay, another thing is I've defined n to be odd if there exists an integer k such that n is equal to 2 times k plus 1. Okay, an alternate definition in an alternate universe is I might have said we say n is odd if it is not even. And there are benefits and drawbacks to each of these definitions. Okay, so what is a drawback to our current definition, where n is even if it's 2 times k, n is odd if it's 2 times k plus 1? Well, one thing about our current definition is that from this definition, we do not know that every integer is even or odd, but not both. Because maybe there's some integer that you can't write as 2 times k, or you can't write as 2 times k plus 1, in which case you wouldn't call it either even or odd. Or maybe there's an integer that you can write as 2 times k for some k, and you can also write it as 2 times j plus 1 for some different j. So from our current definition, we would need to prove that every integer is even or odd, but not both. But in this alternate universe definition, where I said n is odd if n is not even, you would know already that every integer is either even or odd, but not both, because odd just means not even. So why did I choose the first definition rather than the second definition? The nice thing about the first definition is that if you have an odd integer, you can do something concrete with it. So if you're in the middle of a proof and you know that n is odd, you can automatically write, oh, then there exists an integer k, it's just that n is equal to 2k plus 1. So it gives you something concrete to work with. If I use this alternate universe definition, if you knew that n was odd, all you would know is, oh, n is not even, so I can't possibly write it as 2 times k. But that's not a concrete thing to work with. So I think the first definition is more convenient to work with. However, we don't right now know that every integer is even or odd, but not both. We'll actually have to prove that, and we'll prove it next time. Okay, in fact, right now, we don't know that any integers are either even or odd. It's possible, just from this definition, that no integers are even and no integers are odd. Of course, that's not true. The first theorem that we should prove is just that 1 is odd. And the proof is just that this is an immediate proof, since 1 is equal to 2 times 0 plus 1. Because 0 is you prove that 2 times 0, or anything times 0 is 0, and 0 plus anything is that thing. So we actually worked a little bit to make sure that this equation holds. But now it satisfies the definition of being odd. Notice that if we had gone with the alternate universe definition, to prove that 1 is odd, you'd have to prove that there's no possible k such that 1 is equal to 2 times k, which is a little bit harder to prove, right? That would require something more complicated than this. Okay, but the last theorem of today that I think we'll have time to cover today is the integer 1 is not even. I just said that this would be kind of hard to prove, because now we need to prove that no matter which possible integer k you pick, you'll never get that 1 is equal to 2 times k. Let's prove it. So suppose for contradiction, we'll do a contradiction proof that there exists an integer k such that 1 is equal to 2 times k. So I'm going to try to reach a contradiction. And what I'll do here is I'll break into cases. Okay, and cases, that's already a technique we've used, but I think I've not formally introduced it. So after this proof, I'll write the technique down formally. Okay, but there are 4 possible cases. And what I'll do is I'll arrive at a contradiction in every possible case, which means that no matter what the case is, there's a contradiction, which must mean that the thing that I'm supposing is false. Okay, so there are 4 cases. So case 1, let's call this case k is positive. Right? I'm assuming that there exists an integer k. Sorry, k is negative. The cases I'm going to break into are basically k is negative, k is positive, and k is 0. But I'll break into even more cases than that. Okay, well, if k is negative, then by definition, negative k, the additive inverse of k, is positive. So 2 times negative k is positive by closure of the positives. Right, but 2 times negative k equals negative 2k. It's the additive inverse of 2 times k. This is by, I guess, a homework exercise. Therefore, since negative 2k is positive, 2k is negative. But remember, 2k equals 1. So here I'm saying that 1 is negative, but we already proved that 1 is positive, which is a contradiction by trichotomy. Every number is positive or negative or 0, exactly one of them. So it can't be both positive and negative. Okay, maybe actually we've never discussed why 2 is positive, but 2 just means 1 plus 1. That's what we mean by the number 2. And 1 is positive, we proved that. And then by closure, 1 plus 1 is positive. Okay, case 2 is k equals 0. Okay, but if k equals 0, then we already showed that 2 times k, which is 2 times 0, is 0. We proved that already. Anything times 0 is 0. But remember, again, 1 is 2k, right? So 0 equals 1, but the identity axiom asserted that 0 and 1 were different numbers. So this is a contradiction. I can't have that 0 equals 1, but also 0 does not equal 1. Okay. Case 3, let's say that k equals 1. So I'm going to handle this case differently from the rest of the positive numbers. Okay, so if k equals 1, then 2 times k is 2 times 1. That's 2, because 1 is the multiplicative identity, which means that 1 equals 2, right? Because 2k is supposed to equal 1. But now what I can do is I can add negative 1 to both sides using a theorem that we proved that you can add the same thing to both sides of an equality. So that was theorem 38 in your notes. To add 1 to both sides, negative 1 to both sides, yields 0 equals 1, which is again a contradiction, as we discussed above. And then what's the only remaining case? I've supposed that k is negative, k is 0, k is 1. The only remaining case is that k is positive, but not 1. So k is positive, but k is not equal to 1. But we prove that 1 is the smallest positive integer, which means that if k is not equal to 1 and k is positive, then k is greater than 1. So since 1 is the smallest positive integer, therefore k is greater than 1. It's the positive integer that's not 1. And now, by a problem set exercise, which you will do, we can multiply by 2 on both sides, which means that 2k is greater than 2. But remember, 2k is 1, so 1 is greater than 2. But this now contradicts that 1 is the smallest positive integer, because we already discussed that 2 is a positive integer, and it's small. Here I've shown that it's smaller than 1. So since 2 is positive, this contradicts that 1 is the smallest positive integer. Okay, and so since I've reached a contradiction in every possible case, this means that I've reached a contradiction overall, which means the thing that I suppose for contradiction must be false. So in any case, there's a contradiction. Hence, 1 is not even. So 1 is odd, but 1 is not even, is what we spent 2 slides trying to prove, which, yet again, if your roommate is listening to you take this math course, they'll be like, what the heck are you doing? Everyone knows that 1 is odd, but not even. But then ask them, how do they know that? They're not going to know why. They're not even going to know the definition of even and odd, maybe, right? Okay, but this is now like the second or third time that I've broken into cases. So I think it's worth just in your notes writing down what this technique is. So let's call this breaking into cases. Because there is something I want to say about this. So to prove that something is true, prove that it is true in specific cases, as long as those specific cases exhaust all possible cases. Okay, so breaking into cases is nice because it lets you assume something more in order to prove something. Right, so here I was trying to reach a contradiction. In the second case, I got to assume that k was 0. So I got to actually use something about k. So it gave me something to work with. But of course, then I've only proved it in that specific case. But as long as my cases cover all the possibilities, then it's true overall, because no matter what the possible case is, the statement is true. So the thing about casework is that you need to make sure that it's clear to the reader what your cases are. And you also need to make sure it's really clear that the cases cover all possibilities. So k is negative, k is positive, or k is 0. Those are all the cases by trichotomy. And then k being positive, either it's 1 or it's not 1. So I think it's pretty clear that these 4 cases cover all possibilities for the integers, positive integers, not for the integers. But if it's ever not that clear to the reader, you need to make it really clear why your cases cover all possibilities. Okay. As another example, so for example, to prove something about all integers n, maybe you'll have case 1, n is negative, case 2, n is 0, case 3, n is positive. And by trichotomy, this will be all the cases. Okay, but later on in this course, maybe you'll have case 1, n is even, case 2, n is odd. Right now, we don't know that these 2 cases cover all possibilities. I've sort of hammered this point when I made the definition of even and odd. We don't know that every integer is even or odd, but not both. But we will soon. In the next lecture, we'll prove that. In which case, then you can break into these 2 cases, which is nice because when you prove this case, you'll get to assume something about n. You prove this case, you'll get to assume something about n. You prove that it's true in both cases, then it's just true for every positive integer. Okay, but again, you have to make clear that your cases cover all possibilities. And if you go back and look at where we've done casework in this class so far, you'll see that we have done that. Okay, so it's a very, very common technique in mathematics, which you will use many, 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 many times over your time at UW. But it's worth making some comments about it here because we're sort of already using it. Okay, so next lecture, we'll continue in chapter 3. There might even be 2 more lectures on chapter 3, depending on how fast things go. And then we'll move into chapter 4, etc. All right.